This talk is entitled Visualizing Group Theory, and I gave it at MathFest during 2009 in Portland, Oregon, and this is a recap of it for the web. The purpose of this talk is to show you the value of visualization in group theory. There's lots of ways to do that, but here's what I'm going to focus on in this talk. Specifically, the visualization technique I'm going to use is Cayley diagrams. There are lots of different ways to visualize groups, but that is one of the most effective, and I'll show you why in this talk. And if you want to see some of the basics of how to visualize Cayley diagrams, there's another talk on this same website that you can see that covers that. I'll cover just a brief introduction in this talk, and you can see the other one for more information. We're going to cover direct products and quotients so that you can see a quick introduction to how those things get visualized with animated Cayley diagrams. And that naturally leads us to the question, well, can you visualize more sophisticated stuff than that, or is visualization just for these introductory topics? So I want to move on from a direct product to a semi-direct product, a more complex concept, and show that indeed you can visualize more interesting, more intricate topics from group theory, and that it's really beneficial to do so. It really clarifies the topic. So we'll need to learn about automorphism groups and homomorphisms in order to get to semi-direct products, which is going to be sort of the focal point of the end of this talk. So a Cayley diagram is a graph, like the one shown here, where the nodes represent the elements of the group, and the arrows that connect them show how the generators act on the group. So this is the cyclic group of order 3, and the red arrow represents adding 1 mod 3. Right? If you have a group with more than one generator, like the Klein 4 group here, you can just color the arrows to show which generator they represent. So we have the red generator and the green generator here. And in this particular group, the arrowheads have been removed because all the generators are of order 2. On an order 2 generator, it's not necessary to include the arrowheads because it's a two-way street. Cayley diagrams really faithfully represent the group. For example, when we talk about cyclic groups, the Cayley diagrams look like cycles. It's very appropriate. Here you can see the Cayley diagram of a group of order 3, the cyclic group of order 3, cyclic group of order 5, and the general pattern for any cyclic group. They also faithfully represent dihedral groups. Dihedral groups are those that are the symmetries of regular polygons. Here's the symmetries of a triangle, an equilateral triangle, the group of symmetries of a regular pentagon, and the group of symmetries of a regular n-gon. The outer cycle represents just rotating the polygon, and then the blue connectors represent flipping the polygon over, so that the inner cycle is rotating it after it's been flipped, and you can see that that cycle goes the other direction, because when you flip the polygon over, clockwise becomes counterclockwise and vice versa. So this is a really faithful representation of what the group looks like, and I'm using faithful in the ordinary English sense there, not the technical math sense. However, Cayley diagrams can get quite intricate, but even so, they still are a good representation of the group. Here's a Cayley diagram for the group A5, which is the symmetries of the icosahedron. In fact, this Cayley diagram is laid out like a truncated icosahedron, and that's no coincidence. This group is representing the thing that it is the symmetries of. This diagram surely would be easier to see and understand if you could see it sort of rotating in 3D. And you can. I'll give you a link at the end of this talk to some software you can get that will allow you to interactively explore not just these diagrams, but how to rearrange them, how to highlight subgroups in them, how to make homomorphisms among them, etc. So now that we've seen what Cayley diagrams can do, let's see if we animate them, how we can see processes about groups and how they relate to each other. Let's start with the simplest way to construct larger groups from smaller ones, a direct product. Here I'm going to construct the direct product of the cyclic group of order 3 on the left with the cyclic group of order 4 on the right. And to do that, first I'm going to straighten out both of these cycles into straight lines because it just makes the visuals easier to see. So what I'm going to do is I'm going to inflate the nodes of the diagram on the left so that I can put multiple copies of the diagram on the right into them. There was the multiplication that just took place. We multiplied nodes, and now we also need to multiply arrows in order to connect all those new nodes we just made. But we multiply them directly. You see the connections are straight across. So now I don't need those large guide nodes anymore. I can get rid of them, and we have constructed a direct product group. you can see that one axis is formed by the one group and the other axis is formed by the other group. So we have the one group times the other group. So direct product is easy to visualize. What about a quotient? Here is a group. This is a Cayley diagram for A4, and you can see that it has inside it a subgroup isomorphic to the Klein 4 group. So here's a little copy of the Klein 4 group we saw earlier inside this larger group, and this is one of its cosets and this is another. They're identical copies of the subgroup, but they don't contain the identity. Now, the quotient process is the opposite of product process, so instead of multiplying nodes and arrows, we're going to be combining them. For example, these 4 arrows unanimously take that subgroup to its first coset. So I'm just going to simplify and throw away some information here and call all those arrows 1. They go from the top to the right. And these 4 arrows go from the right to the left, so I'll just call them 1 arrow from right to left, and similarly I'll combine these 4 arrows. If the arrows had not agreed that they would all go from this coset to this one and this coset to this one and so on, if they had some arrows leaving here gone to there and some arrows leaving here gone to there, then this subgroup would not be normal and I could not do this quotient process. But because the arrows were unanimous about how they flowed through this little cycle of 3 cosets, I can simplify in this way, and then I can even take the cosets and just sort of combine them into single nodes, and now I have undone the multiplication of nodes and arrows that a product would have done, and constructed this cyclic group of order 3. So we've revealed this simple cyclic structure inside the more complicated A4 structure. But A4 was not constructed by a direct product. What kind of product was it constructed by? Well, a semi-direct product, and that's what we're going to learn about now. A semi-direct product has a more complicated definition than a direct product. Here's the definition as you would see it in a typical group theory textbook. But the value of visualization here is that we don't need to read and understand all these details, especially that particularly intricate last equation there, in order to visualize it. In fact, visualizing it first can help us then come back and take a look at this technical definition and understand it better, because we have some intuition as a foundation on which to ground our careful reading of this definition. So let's begin by just learning about how to visualize the parts of this definition. We'll start with an automorphism group. The way I think of automorphisms is as what I call rewirings. A rewiring of a Cayley diagram is a way that you rearrange the arrows but not the nodes, and do not alter the algebraic structure of the diagram. So for example, here we have a diagram of the cyclic group of order 3 from before. If we rearrange its arrows like this, well, that doesn't even form a group, so that certainly doesn't count as a rewiring. But for example, if we just rearrange the arrows by reversing all of them, that counts as a rewiring because the algebraic structure hasn't changed. And what do I mean by that? Well, I mean that all the equations that you could write that are true from one of these diagrams is still true in the other one. So from the point of view of algebra, nothing's changed. Another way to say that is that these 2 diagrams would give rise to the same multiplication table. So one way to rewire the Cayley diagram on the left is simply to reverse its arrows. And reversing them again gets you back to the Cayley diagram on the left again. So I can form a little group whose actions are the ways to rewire the cyclic group of order 3. It's a very small group. It's a group with just these 2 elements. Right? Some rewiring groups are larger. For example, the rewiring group of the Klein 4 group has 6 elements. And I'm not going to go through the process of how you find all of them, but those the actions in this group are permutations of the arrows in the diagram, leaving the nodes in place. And so there are 6 different rewirings, and they're connected by arrows, and this legend here indicates how you can see the horizontal, vertical, and diagonal arrows being permuted. So now that we understand what automorphism groups are, or at least understand how to visualize them, let's talk about homomorphisms, because we need to be able to write a homomorphism into an automorphism group in order to be able to construct a semi-direct product. Well, in an ordinary group theory textbook that does not use visualization, a homomorphism would be defined this way. This is the algebraic way to specify what it means to have a function that preserves group structure. Well, visually, we're still going to be talking about a function that preserves group structure, but instead of writing out an equation for it, I'll tell you what preserving group structure looks like. Let's say we want to create an automorphism from the cyclic group of order 3 over to the cyclic group of order 6. All right? So the first thing about preserving group structure is that the special element of the identity needs to be preserved. So we have to map the identity to the identity. So that's what that arrow indicates. Secondly, whatever I do with this mapping I have to be consistent with. So for example, if I choose to map 1 to 2, and I've chosen that because I know it's going to work out and create a homomorphism, as you'll see in a minute, what I've done there is I've mapped this red arrow in the domain to these 2 red arrows in the codomain. Right? That's what these 2 black dotted lines effectively accomplish. They map this red arrow over to this red arrow. Okay? So I need to be consistent with that definition I've made. This red arrow here needs to also map to 2 red arrows. Right? So I'm forced now to connect 2 to 4 in order to make that happen. And this red arrow is forced to map to these 2 red arrows, but that actually already works out because I've already mapped 0 to 0. If I had chosen to map 1 to something different, like tried to map 1 to 1, I would not have come around to having this work out as a homomorphism. I wouldn't be mapping 0 to 0. I would have eventually come down and been forced to map 0 also to 3, which isn't even a function, so that's why you can't map 1 to 1 and have a homomorphism. So if I map the identity to the identity, and I'm consistent with the other mappings I make, that's a homomorphism. That's what preserving group structure means. So, for example, this can happen in, that example was an embedding. Here's an example with a quotient map. In this case, we're mapping these red connectors in the domain to the red connector in the codomain, and we're mapping these green connectors in the domain to the empty map in the codomain. Right? So still, we're being consistent. All the red connectors go to the same place, all the green connectors go to the same place. So this is what preserving group structure looks like visually. So we understand homomorphisms now into automorphism groups, so we can use that to understand semidirect products. We don't even need to understand this equation in order to visualize it. We can come back later and understand that equation based on what we learned from visualization. So let's construct this semidirect product of the cyclic group of order 3 with the Klein 4 group. And when you construct a semidirect product, you have this particular homomorphism you're going to use to construct the semidirect product. It's a homomorphism from this group into the automorphism group of this one. Recall what the automorphism group of Klein 4 group looks like. It looks like this. So I need a homomorphism from the cyclic group of order 3 into that automorphism group. Here's the simplest such automorphism. It just maps this blue ring to the outer blue ring here. So I'll throw away all the other stuff from the codomain that I don't need. And now I'm going to use those 3 rewirings that I selected with this automorphism to replace the nodes in the domain. And now that I've done so, I can do just what I did in the direct product. Multiply the arrows and make them direct connections across. Now in the direct product we had direct connections among identical things, but here these direct connections among non-identical things actually do create a tangled structure. In fact, if I were to take each of these rewirings down here and unrewire it so that it looks like the original, then the arrows themselves would get tangled up in the process, and I would construct the Cayley diagram that we saw earlier for the group A4. So we've shown here that A4 is a semidirect product of the cyclic group of order 3 with the Klein 4 group, using the particular homomorphism that I selected earlier. So, group theory visualization is not just for visualizing the basic stuff of group theory. You can do intricate stuff with it too, like semidirect products, like we just saw. But you can also do other interesting topics. Here are some of them. The other talk on this website covers the first 3, and if you want to see more about the last one, then I'll refer you to some other references. First of all, if you're interested in the free software for group theory visualization I mentioned earlier, that's Group Explorer, available at that URL. If you're interested in a book that covers all of these topics and more, then I have a book entitled Visual Group Theory. You can see it on this website, and when I gave this talk at MathFest, I was suggesting people go check it out at the booth in the exhibit hall. And these videos and other ones are available on the website at which you found this video, and I'm currently thinking about how to extend the discussion and animation of products in this talk to cover the more general knit products. Anybody with any feedback or ideas or input on that is welcome to send me an email. Thank you.